Hello there, and welcome to The Sleepy Mathematician, where the mysteries of the universe unfold gently in the quiet hours of the night. Tonight we're embarking on a journey to one of the most enigmatic and mind-bending phenomena in all of physics, the event horizon, that invisible threshold around black holes where space and time themselves become so twisted that even light cannot escape. I'm so glad you found your way here tonight. Whether you're tucked into bed with the lights dimmed low, curled up on your favorite couch, or simply seeking a peaceful moment to let your mind wander among the stars, this is your space. A gentle corner of the cosmos where curiosity meets tranquility, and where the most profound mysteries of existence can wash over you like a warm cosmic tide. Before we drift into the depths of space-time itself, I'd love to know where you're listening from tonight. Are you watching from a quiet bedroom in Tokyo as dawn approaches? Perhaps it's late evening in London, or maybe you're somewhere in between, in that perfect twilight hour when the day's worries begin to fade. Drop a comment and let me know where in the world you are right now. There's something beautifully poetic about the fact that while we explore these cosmic boundaries together, we're scattered across our own earthly time zones, each experiencing this moment in our own unique slice of the clock. Now, I should mention that while I've crafted tonight's journey to be as soothing and sleep-friendly as possible, the event horizon is genuinely one of the most fascinating concepts in all of physics. So if you find yourself unexpectedly captivated by these cosmic mysteries, don't worry, sometimes the most beautiful way to fall asleep is with your mind gently buzzing with wonder about the universe. And if you do drift off partway through, well, that's perfectly wonderful too. If you're enjoying this peaceful exploration of the cosmos, I'd be ever so grateful if you could give this video a gentle like and perhaps subscribe to join our community of sleepy scientists. It helps more curious minds like yours find their way to this quiet corner of YouTube, where science meets serenity under the vast canopy of night. So settle in, take a slow, deep breath, and let your thoughts begin to float freely. Tonight, we're going to explore something that challenges everything we think we know about reality itself. The event horizon isn't just a boundary in space. It's a boundary in our understanding, a place where the familiar laws of physics stretch and bend into something almost unrecognizable. Imagine, if you will, standing at the edge of a cosmic cliff. But this isn't an ordinary cliff with rocks and dirt and a view of the landscape below. This is a cliff in space-time itself, where the very fabric of reality drops away into something so profound, so fundamentally different, that crossing it would separate you forever from the universe you've always known. That's what we're exploring tonight, the strange truth about the event horizon. Let's begin our gentle descent into this cosmic mystery by first understanding what we're actually talking about when we speak of an event horizon. Picture space not as the empty void we often imagine, but as a flexible fabric, like a stretched rubber sheet. When you place a heavy ball on this sheet, it creates a depression, a curve in the fabric. Now imagine a ball so incredibly heavy, so dense, that it creates not just a gentle dip, but a steep-sided pit that curves inward so sharply that anything rolling toward it would inevitably fall in, never to return. This is essentially what happens when a massive star, many times heavier than our sun, reaches the end of its life. When such a giant runs out of fuel, it can no longer support itself against its own immense gravitational pull. In a catastrophic collapse that takes mere seconds, all that mass gets compressed into a point of infinite density that physicists call a singularity. The gravitational field around this singularity becomes so intense that it warps space-time to an extreme degree, creating a region from which nothing, not even light itself, can escape. The boundary of this region is what we call the event horizon. It's not a physical surface you could touch or see directly. Rather, it's an invisible sphere of influence surrounding the black hole's center, marking the point of no return. Once anything crosses this threshold, its fate is sealed. It will inevitably spiral inward toward the singularity, and no force in the universe can pull it back out. What makes this boundary so remarkable is that it's defined by one of the fundamental constants of our universe, the speed of light. We often think of light as the fastest thing possible, racing through space at nearly 300 million meters per second. Nothing with mass can travel faster than this cosmic speed limit. Yet, at the event horizon, even light moving at its maximum speed cannot escape the black hole's gravitational embrace. This creates something truly extraordinary. A one-way membrane in space-time. Information, matter, energy, everything that falls past this boundary becomes forever cut off from the rest of the universe. It's as if a cosmic curtain falls, separating the interior of the black hole from everything else that exists. The size of this boundary depends entirely on the mass of the black hole that creates it. For a black hole with the same mass as our Sun, the event horizon would have a radius of only about 3 kilometers. That's smaller than most cities, yet it would represent the boundary around an object whose gravitational influence could be felt across vast distances. Double the mass of the black hole, and the event horizon doubles in size as well. This simple relationship means that the supermassive black holes lurking at the centers of galaxies, containing millions or billions of times the mass of our Sun, possess event horizons that could engulf entire solar systems. But here's where things become truly mind-bending. The event horizon reveals something profound about the nature of time itself. As you approach a black hole, time doesn't just slow down slightly, as you might experience in other gravitational fields. Near the event horizon, time dilation becomes so extreme that it creates what can only be described as a temporal paradox. Imagine you're watching a friend fall toward a black hole. As they approach the event horizon, something extraordinary happens from your perspective. Their movements appear to slow down dramatically. Their watch seems to tick more and more slowly. The light from their body becomes increasingly stretched toward longer, redder wavelengths until it fades beyond what your eyes can detect. From your vantage point, they never actually cross the event horizon. They appear to freeze at the boundary, their image growing dimmer and redder until it vanishes entirely, but never quite crossing that invisible line. Yet from your friend's perspective, something completely different occurs. They experience time normally as they fall. They don't feel themselves slowing down. In fact, for supermassive black holes, crossing the event horizon might feel surprisingly mundane at first. There's no dramatic moment, no sudden change, no wall to crash through. They simply pass through this invisible boundary in what feels like normal time, continuing their journey inward toward the singularity. This duality reveals something profound about the nature of reality itself. The same event, observed from different reference frames, appears completely different. Both perspectives are equally valid within the framework of Einstein's relativity, yet they seem to describe entirely contradictory situations. This isn't a flaw in our understanding, it's a feature of how space-time itself behaves under extreme conditions. The mathematical description of this phenomenon emerged just months after Einstein published his theory of general relativity in 1915. A German physicist named Karl Schwarzschild, tragically working on the problem while serving on the Russian front during World War I, found an exact solution to Einstein's field equations. Schwarzschild died of an autoimmune disease contracted during the war just months after making this discovery, but his solution would become one of the most important in all of theoretical physics. The Schwarzschild solution revealed that for any object, if you could compress it down to a certain critical radius, now called the Schwarzschild radius, it would become a black hole. For Earth, that radius would be about 9 millimeters. For the Sun, It's those 3 kilometers we mentioned earlier. These numbers seem impossibly small compared to the actual sizes of these objects, which is why black holes are such exotic phenomena requiring the most extreme conditions in the universe to form. What Schwarzschild's mathematics revealed was that space-time itself has a structure, and that structure can be curved and distorted by mass and energy. The event horizon represents a place where this curvature becomes so extreme that it creates a boundary in the very fabric of reality. It's not just that gravity becomes very strong near a black hole, it's that space and time themselves become so warped that the normal rules of cause and effect begin to break down. Inside the event horizon, the roles of space and time become interchanged in a sense. The direction toward the singularity becomes as inevitable as moving forward in time. Just as you cannot travel backward in time in normal space-time, once inside the event horizon, you cannot travel away from the center of the black hole. Every possible path through space-time leads inexorably inward. This geometric inevitability is what makes the event horizon so fundamentally different from any other boundary we encounter in everyday life. You can turn around before reaching the edge of a cliff, or change course before hitting a wall. But the event horizon represents a point where the geometry of space-time itself eliminates all paths that lead back to the outside universe. The discovery of black holes and their event horizons represents one of humanity's greatest intellectual achievements. It began with pure mathematical exploration of Einstein's equations and has evolved into one of the most active areas of observational astronomy. What started as an abstract theoretical concept has become a concrete reality that we can study, measure, and even photograph. Yet despite decades of research, the event horizon continues to pose some of the most challenging questions in all of physics. These questions touch on the fundamental nature of information, the relationship between quantum mechanics and gravity, and even the basic structure of reality itself. As we'll explore in the coming parts of our journey, the event horizon isn't just a boundary around black holes. It's a boundary in human knowledge, marking the edge of what we can observe and understand about our universe. Tonight, as we rest in the gentle embrace of Earth's gravity, we can marvel at the fact that the same force keeping us safely in our beds also creates these most extreme environments in the cosmos. The event horizon stands as a testament to the profound mystery and beauty of the universe we inhabit, reminding us that reality is far stranger and more wonderful than our everyday experience might suggest. As we prepare to delve deeper into these cosmic mysteries in our next segment, let your mind drift gently among the stars, knowing that somewhere out there, invisible boundaries in space-time are quietly marking the edges of the known universe, holding secrets that challenge everything we think we know about existence itself. As we drift deeper into the cosmic mysteries of the event horizon, let's explore something truly extraordinary that emerges from the mathematics of these invisible boundaries. You see, the event horizon isn't just a simple sphere of no return, it's a dynamic, breathing boundary that responds to the black hole's properties in fascinating ways. When we speak of black holes, we often imagine them as perfectly spherical, unchanging objects. But reality, as it so often does, proves far more intriguing. Black holes can spin, and when they do, they drag the very fabric of space-time around with them, like honey swirling around a spoon. This phenomenon, known as frame dragging, creates a region outside the event horizon called the ergosphere, where space-time itself is pulled along with the black hole's rotation. Picture, if you will, standing near a massive carousel that's spinning so fast it creates a whirlwind around itself. Even if you tried to stand perfectly still, you'd be swept along by the rushing air. The ergosphere works similarly, but instead of air, it's space-time itself that's being dragged along. Nothing can remain stationary relative to distant observers in this region, because the very coordinate system is being twisted and pulled by the black hole's rotation. What's remarkable about this region is that it exists outside the event horizon itself. This means that unlike the event horizon, from which nothing can escape, objects can actually enter the ergosphere and still make their way back out to the wider universe. This creates fascinating possibilities for what physicists call energy extraction, where carefully planned trajectories could theoretically allow spacecraft to steal rotational energy from the black hole itself. The mathematical beauty of rotating black holes was first described by Roy Kerr in 1963, and the solution that bears his name reveals layer upon layer of complexity. Unlike the relatively simple Schwarzschild solution for non-rotating black holes, the Kerr metric describes a space-time geometry where the event horizon itself takes on a more complex shape, flattened at the poles like a cosmic pumpkin. But let's pause for a moment and consider something even more fundamental about these boundaries. The event horizon challenges our most basic intuitions about the nature of information itself. In our everyday experience, information can be copied, transmitted, stored, and retrieved. You can write down a recipe, share it with friends, and still keep the original. Information seems abundant and freely shareable. Yet the event horizon appears to create a cosmic shredder for information. When matter falls past this boundary, it carries with it all the information about its quantum state, its history, its very identity. According to classical understanding, this information becomes trapped forever inside the black hole, cut off from the rest of the universe by the one-way nature of the event horizon. This might not seem particularly troubling at first glance. After all, lots of information gets lost in everyday life. Old books crumble, computer files get corrupted, memories fade. But quantum mechanics, our best theory for how the universe works at its most fundamental level, insists that information cannot be destroyed. It can be scrambled, hidden, or transformed beyond recognition, but it must always be preserved somewhere in the universe. This creates what physicists call the information paradox, and it's one of the most profound puzzles in modern science. If black holes can truly destroy information, then quantum mechanics is wrong about something very fundamental. But if information is preserved, then our understanding of event horizons and general relativity might need dramatic revision. The puzzle deepened considerably when Stephen Hawking made his groundbreaking discovery in the 1970s that black holes aren't perfectly black after all. Through a subtle interplay between quantum mechanics and the curved spacetime near the event horizon, black holes actually emit radiation and slowly evaporate over time. Imagine the quantum vacuum, that seething sea of virtual particles that pop into existence and annihilate each other throughout space. Near the event horizon, this quantum foam behaves strangely. Pairs of particles that would normally annihilate each other can be separated by the intense gravitational field, with one particle falling into the black hole while its partner escapes as real radiation. This Hawking radiation, as it's now known, means that black holes slowly lose mass over time, eventually evaporating completely. For stellar mass black holes, this process takes an almost incomprehensibly long time, far longer than the current age of the universe. But for tiny black holes, if they exist, the evaporation would be rapid and explosive. Here's where the information paradox becomes acute. If a black hole evaporates completely through Hawking radiation, what happens to all the information that fell into it over its lifetime? The radiation appears to be completely random, carrying no information about what fell in. Yet quantum mechanics demands that information must be preserved. This paradox has driven some of the most innovative thinking in theoretical physics over the past several decades. Some physicists propose that the information isn't really lost, but is encoded in subtle correlations in the Hawking radiation itself. The information is preserved, but in such a scrambled form that it would take longer than the age of the universe to decode. Others have suggested even more radical solutions. Perhaps the event horizon isn't the smooth, empty boundary that Einstein's equations suggest. Maybe it's actually a seething wall of high-energy particles, a cosmic firewall that incinerates anything attempting to cross it. This would prevent information from ever entering the black hole in the first place, preserving quantum mechanics, but at the cost of violating other cherished principles of physics. The firewall proposal created quite a stir in the physics community because it suggests that the smooth spacetime predicted by general relativity breaks down at the event horizon. An astronaut approaching a black hole wouldn't experience the gentle fall into darkness that relativity predicts. Instead, they would encounter a wall of destruction that would vaporize them instantly upon reaching the horizon. Yet another possibility emerges from the strange world of quantum entanglement, where particles can maintain mysterious correlations across vast distances. Perhaps the information that falls into a black hole doesn't disappear, but becomes entangled with the information in the Hawking radiation in ways that preserve the overall quantum state of the system. This leads us to one of the most mind-bending ideas in modern physics, the holographic principle. This concept suggests that all the information contained within a volume of space can be encoded on its boundary, like a cosmic hologram. Applied to black holes, this means that everything that falls past the event horizon might not really be inside the black hole at all. Instead, it could be encoded as information on the surface of the event horizon itself. If the holographic principle is correct, it has profound implications for our understanding of reality. It suggests that what we perceive as three-dimensional space might actually be an illusion, a projection of information stored on a two-dimensional surface. The event horizon becomes not just a boundary in space, but a boundary between different ways of describing reality. This duality extends to our understanding of what happens when you fall into a black hole. From outside the black hole, an observer would see you slow down and freeze at the event horizon, your information encoded forever on the boundary. But from your perspective as you fall, you would pass through the horizon and continue toward the singularity, carrying your information with you. Both descriptions are valid within their respective frameworks, yet they seem to describe completely different realities. The resolution of this apparent contradiction may require us to abandon some of our most basic assumptions about the nature of spacetime itself. Some physicists propose that spacetime isn't fundamental but emergent, arising from more basic quantum information processing. In this view, the event horizon becomes a place where this emergence breaks down, where the illusion of continuous spacetime gives way to the underlying quantum mechanical reality. String theory, our most ambitious attempt to unify quantum mechanics and general relativity, offers its own perspective on these puzzles. In string theory, black holes can be described as complex configurations of tiny vibrating strings existing in higher dimensional space. The information that falls into a string theory black hole doesn't disappear, but becomes encoded in the string configurations themselves. As we contemplate these cosmic puzzles, it's worth remembering that the event horizon represents more than just an abstract theoretical concept. Recent technological achievements have brought us tantalizingly close to directly observing these boundaries. The Event Horizon Telescope, a global network of radio telescopes working together, has captured the first images of the shadows cast by supermassive black holes, providing direct confirmation of their existence and properties. These observations represent the culmination of decades of theoretical development and technological advancement. What began as purely mathematical speculation has become observable reality, transforming our understanding of these exotic objects and the extreme physics that governs them. The detection of gravitational waves from merging black holes has opened another window into the behavior of event horizons. When two black holes spiral into each other, their event horizons eventually touch and merge in a process that sends ripples through spacetime itself. These gravitational waves carry information about the merger process, providing new insights into how these cosmic boundaries behave under the most extreme conditions imaginable. As we rest here in the gentle quiet of the night, it's remarkable to think that somewhere in the universe, invisible boundaries are marking the edges of the observable, holding secrets that challenge our deepest understanding of reality. The event horizon stands as both a boundary and a gateway, a limit to what we can know and a doorway to new physics waiting to be discovered. Tonight, as your thoughts drift gently among these cosmic mysteries, remember that the same mathematical principles that describe these exotic boundaries also govern the familiar world around us. The curvature of space-time that creates event horizons is present everywhere, even in the gentle gravitational field of Earth that keeps you safely in your bed. We live in a universe where the most extreme and exotic phenomena emerge naturally from the same fundamental laws that shape our everyday experience. In our next gentle exploration, we'll delve even deeper into these mysteries, examining how the event horizon challenges our understanding of time itself and reveals connections between gravity, thermodynamics, and information that continue to reshape our view of the cosmos. As we continue our gentle journey through the mysteries of space-time, let's explore one of the most profound revelations that emerges from studying event horizons: their intimate relationship with the arrow of time itself. You see, near these cosmic boundaries, time doesn't merely slow down or speed up in the way we might imagine. It undergoes a fundamental transformation that challenges everything we thought we knew about causality and the flow of existence. Consider for a moment how we normally experience time. It flows from past to future in what seems like an inevitable river, carrying us along its current. We remember yesterday but not tomorrow. We can influence the future but not the past. This directional quality of time feels so fundamental to our existence that we rarely question it. Yet near an event horizon, even this most basic aspect of reality begins to behave in strange and wonderful ways. The mathematics of general relativity reveal that as you approach a black hole, the distinction between space and time begins to blur in fascinating ways. Far from the black hole, time flows normally, and space extends in all directions as we expect. But as you draw closer to that invisible boundary, something remarkable happens. The coordinate we normally associate with time begins to behave more like a spatial coordinate, while one of the spatial directions takes on time-like properties. This transformation becomes complete once you cross the event horizon. Inside this boundary, the direction pointing toward the singularity at the center becomes as inevitable as the flow of time itself. Just as you cannot travel backward in time in normal space-time, once inside the event horizon, you cannot move away from the black hole's center. Every possible path through space-time leads inexorably inward, making the journey to the singularity as unavoidable as tomorrow's sunrise. This geometric inevitability represents something profound about the nature of determinism in our universe. Outside the event horizon, you have choices about where to go and what to do. You can accelerate, change direction, or even escape the black hole's influence entirely if you have enough energy. But once you cross that threshold, choice itself becomes an illusion. The curvature of space-time has become so extreme that all futures converge on a single destination. Yet this raises fascinating questions about the nature of experience itself. If someone falls past the event horizon, do they continue to experience the passage of time normally as they journey toward the singularity? The mathematics suggests they would, at least initially. For supermassive black holes, an astronaut might have hours or even days of subjective time after crossing the horizon before reaching the center. During this interval, they could still think, observe, and experience their surroundings, even though their fate is sealed. This creates a poignant philosophical puzzle. In those final moments of existence, would the astronaut retain their sense of agency and consciousness? Would they be aware that no signal they could send would ever reach the outside universe? From their perspective, they would be living through real moments of time, having genuine experiences and thoughts, yet these experiences would be forever cut off from the rest of reality. The thermal properties of event horizons add another layer of mystery to our understanding. Stephen Hawking's discovery that black holes emit radiation revealed that these boundaries have temperature, much like any other thermal object. But this temperature has an unusual property. It's inversely related to the black hole's mass. Smaller black holes are hotter, while larger ones are colder. For a black hole with the mass of our Sun, this temperature would be incredibly tiny, about 10 million times colder than the cosmic microwave background radiation that fills all of space. Such a black hole would actually absorb more energy from its surroundings than it radiates away, causing it to grow rather than shrink. Only in the far future, when the universe has expanded and cooled significantly, would stellar mass black holes begin to evaporate through their thermal radiation. But imagine, if you will, a microscopic black hole with the mass of a mountain. Such an object would have a temperature of trillions of degrees and would evaporate in a brilliant flash of energy in a fraction of a second. The event horizon around such an object would exist for only the briefest moment before disappearing entirely, taking with it all the information that had fallen inside. This evaporation process creates what many consider the most important unsolved problem in theoretical physics. As the black hole radiates away its mass and eventually disappears completely, what happens to all the information that crossed the event horizon during its lifetime? The radiation appears to carry no memory of what fell in, suggesting that information is truly destroyed. Yet quantum mechanics insists this cannot happen. Some physicists have proposed that the information isn't really destroyed, but is preserved in subtle quantum correlations between the early and late radiation emitted by the black hole. The information would be scrambled beyond practical recovery, but it would still exist in principle. Others suggest that the event horizon itself might not be the smooth boundary we imagine, but rather a complex quantum structure that processes and preserves information in ways we don't yet understand. These debates have led to remarkable insights about the fundamental nature of space-time itself. Some researchers now believe that space and time might not be basic features of reality, but rather emergent properties that arise from more fundamental quantum information. In this view, the event horizon becomes a place where the usual description of space-time breaks down, revealing the deeper informational structure that underlies all of existence. The connection between event horizons and thermodynamics has also revealed surprising relationships between black holes and familiar thermal systems. The entropy of a black hole, which measures how much information it contains, is proportional to the area of its event horizon rather than its volume. This seems counterintuitive at first, since we normally expect the amount of information in a system to depend on how much space it occupies. Yet this area law for black hole entropy has profound implications. It suggests that the event horizon acts like a cosmic hard drive, with each unit of area on the boundary capable of storing a fixed amount of information. This leads to the startling possibility that all the information about what's inside a black hole might actually be encoded on its surface, like a holographic image projected onto the boundary. If this holographic principle is correct, it would mean that the three-dimensional interior of the black hole is somehow equivalent to information stored on its two-dimensional surface. This isn't just a mathematical curiosity, it hints at something fundamental about how information and geometry are related throughout the universe. Perhaps all of space, not just the region inside black holes, might be holographic in nature. The study of rotating black holes has revealed even more exotic properties of event horizons. When a black hole spins, it drags space-time around with it, creating a region called the ergosphere, where nothing can remain at rest relative to distant observers. Within this region, it's actually possible to extract energy from the black hole through carefully orchestrated maneuvers, in principle allowing advanced civilizations to use rotating black holes as cosmic power sources. The boundary between the ergosphere and the event horizon creates fascinating dynamics. Matter spiraling inward can follow trajectories that allow it to gain energy from the black hole's rotation before escaping back to infinity. This process, known as the Penrose mechanism after the physicist Roger Penrose who discovered it, shows that event horizons aren't simply one-way drains but complex boundaries with rich physical structure. Modern observations have begun to reveal these theoretical predictions in action. The Event Horizon Telescope has captured images of the glowing matter swirling around supermassive black holes, showing how material heats up and accelerates as it approaches the event horizon. These observations provide our first direct glimpses of how matter behaves in the extreme gravitational environment near these cosmic boundaries. Similarly, gravitational wave detectors have observed the final moments as pairs of black holes spiral together and merge. In these cosmic collisions, the event horizons of the two black holes eventually touch and combine, creating a larger black hole surrounded by a single unified horizon. The gravitational waves produced during this merger carry information about how these boundaries behave when subjected to the most extreme dynamics imaginable. As we observe these cosmic events, we're essentially watching space-time itself undergo dramatic transformations. The merger of two event horizons represents a fundamental change in the causal structure of the universe as two separate regions of no return combine into one. The gravitational waves that ripple outward from such events are literally distortions in the fabric of space-time, carrying news of these boundary changes across the cosmos at the speed of light. These observations also provide new tests of our theoretical understanding. The gravitational wave signals match the predictions of general relativity with extraordinary precision, confirming that our mathematical description of event horizons accurately captures their behavior even under the most extreme conditions. Yet they also raise new questions about the quantum nature of these boundaries and how they might behave when quantum effects become important. The event horizon continues to serve as a natural laboratory where our most fundamental theories meet and sometimes clash. It represents the boundary between the classical world described by Einstein's relativity and the quantum realm governed by uncertainty and probability. Understanding how these two descriptions of nature fit together at the event horizon remains one of the great challenges in theoretical physics. As you rest here in the gentle embrace of Earth's gravity, consider that the same geometric principles that create event horizons also shape the familiar world around you. The curvature of space-time that becomes so extreme near black holes is present everywhere, creating the gravitational fields that keep planets in their orbits and your feet firmly planted on the ground. We inhabit a universe where the most exotic phenomena emerge naturally from the same mathematical laws that govern everyday experience. The event horizon reminds us that reality is far richer and stranger than our daily experience suggests. These invisible boundaries in space-time represent places where the universe reveals its deepest secrets, where the familiar concepts of space, time, and causality are stretched to their limits and beyond. They stand as monuments to both the power of human reason to uncover nature's hidden workings and the profound mysteries that still await our understanding. Tonight, as your thoughts drift gently among these cosmic puzzles, remember that somewhere in the vast darkness, event horizons are quietly marking the boundaries of the knowable universe, holding within their invisible embrace secrets that continue to challenge our deepest understanding of existence itself. In the profound silence of space, where distances are measured not in kilometers but in the time it takes light to traverse the cosmic dark, we find ourselves contemplating something truly extraordinary about the nature of observation itself. You see, the event horizon presents us with what might be the ultimate puzzle about the relationship between knowledge and reality, between what exists and what can be known to exist. Consider this gentle paradox that emerges from the mathematics of black holes. When we observe distant galaxies through our telescopes, we're seeing them not as they are now, but as they were when their light began its journey to us millions or billions of years ago. This delay is usually quite manageable in our understanding of the universe, but near an event horizon, this relationship between observation and reality becomes stretched to its absolute breaking point. Imagine watching a clock fall toward a black hole. As it approaches the event horizon, something remarkable happens to the light reflecting from its face. Each photon carrying the image of the clock has to work harder and harder to escape the black hole's gravitational embrace. The light becomes increasingly redshifted, stretched to longer wavelengths as it climbs out of the deepening gravitational well. From your safe vantage point, you would see the clock's hands moving more and more slowly. The seconds would stretch into minutes, the minutes into hours. The clock face would grow dimmer and redder as its light is stretched beyond the visible spectrum. Eventually, the image would fade entirely, leaving no trace that the clock ever existed. Yet according to the mathematics, the clock never actually crosses the event horizon from your perspective. It remains frozen at that boundary for eternity, its final moment preserved forever in increasingly faint light. But here's where the mystery deepens. From the clock's own reference frame, from its own experience of time, something completely different occurs. It crosses the event horizon at a specific moment, continues falling inward, and eventually reaches the singularity at the center. The clock experiences its own destruction in finite time, while outside observers see it frozen forever at the boundary. This isn't simply a matter of different perspectives on the same event. These are genuinely different descriptions of reality that seem impossible to reconcile. Both are correct within their own frameworks, yet they appear to describe entirely contradictory outcomes. The event horizon creates a fundamental split in the description of reality itself. This observational puzzle extends to the very nature of the event horizon's existence. If nothing ever crosses the boundary from the perspective of outside observers, in what sense can we say that black holes have interiors at all? Perhaps what we call the interior is simply a mathematical artifact, a region that exists only in the reference frame of infalling observers who can never report back about their experiences. Some physicists have suggested that this observational limit reveals something profound about the nature of reality itself. Perhaps the universe is fundamentally about information and its processing rather than about objects moving through space and time. In this view, the event horizon represents a boundary in information space, a place where different observers literally inhabit different realities. The quantum mechanical description of event horizons adds another layer of mystery to this puzzle. Near the boundary, the intense gravitational field affects the quantum vacuum itself, that seething sea of virtual particles that exists everywhere in space. Normally, these virtual particles appear in pairs and quickly annihilate each other, leaving no lasting trace. But near the event horizon, the curvature of space-time can separate these pairs, allowing one particle to escape while its partner falls inward. This process creates what we observe as Hawking radiation, a thermal glow emanating from the black hole's vicinity. The escaping particles carry energy away from the black hole, causing it to slowly evaporate over cosmic time. But this radiation appears to be completely random, carrying no information about what has fallen into the black hole during its lifetime. Here we encounter another profound mystery. If the Hawking radiation is truly random, then information about anything that fell into the black hole would be permanently lost when the black hole finally evaporates completely. This would violate one of the fundamental principles of quantum mechanics, which insists that information cannot be destroyed in any physical process. The resolution of this information paradox may require us to completely reconceptualize our understanding of what happens at the event horizon. Some physicists propose that the radiation isn't actually random, but contains subtle correlations that preserve the information in scrambled form. Others suggest that the event horizon itself might be far more complex than we imagine, perhaps containing a kind of quantum memory that stores information about everything that has ever approached it. One of the most intriguing proposals is that the event horizon acts as a holographic boundary, encoding all the information about the black hole's interior on its two-dimensional surface. In this view, the three-dimensional interior that we imagine doesn't really exist as a separate space. Instead, it's a kind of projection or shadow of information stored on the boundary itself. This holographic principle, if correct, would have implications that extend far beyond black holes. It suggests that all of space might be holographic in nature, with the information describing any volume actually encoded on its boundary. This would mean that our everyday experience of three-dimensional space is itself a kind of illusion, a projection from a more fundamental two-dimensional reality. The mathematical beauty of this idea is matched by its strangeness. It implies that when you reach out to touch something, you're not actually interacting with a three-dimensional object, but with information encoded on a distant boundary that your brain interprets as occupying the space around you. The event horizon would thus be not just a boundary around black holes, but a window into the fundamental structure of reality itself. Recent advances in quantum error correction have provided new insights into how information might be preserved near event horizons. Just as quantum computers use sophisticated codes to protect information from environmental interference, the event horizon might employ natural quantum error correction to preserve information even under the most extreme conditions imaginable. The mathematics of these error-correcting codes reveal deep connections between information theory, geometry, and gravity. They suggest that spacetime itself might be an emergent phenomenon arising from more fundamental quantum information processing. In this view, the smooth geometry of Einstein's spacetime is like the surface of a deep ocean, with quantum information dynamics playing the role of the hidden currents beneath. This perspective casts the event horizon in a new light. Rather than being a simple boundary in space, it becomes an interface between different levels of description of reality. On one side, we have the familiar world of classical spacetime, where objects have definite positions and follow predictable trajectories. On the other side lies a quantum realm where information is the fundamental currency and geometry emerges from patterns of entanglement and correlation. The study of quantum entanglement near event horizons has revealed surprising connections between distant regions of space-time. When particles become entangled and one falls into a black hole while the other escapes, they maintain their quantum correlation despite being separated by the event horizon. This suggests that the boundary might not be as absolute as classical physics implies. Some researchers have proposed that these entanglement connections might provide a way for information to leak out of black holes, preserving the principles of quantum mechanics while respecting the causal structure imposed by general relativity. The information wouldn't escape in the classical sense, but would be encoded in subtle quantum correlations that span the event horizon. These ideas lead to fascinating speculations about the nature of spacetime itself. Perhaps the event horizon isn't really a boundary at all, but rather a kind of quantum interface where information is processed and transformed. The apparent loss of information might be an illusion created by our limited perspective, like a magician's trick that seems impossible until you understand how it's performed. The firewall proposal represents another attempt to resolve these paradoxes, though it comes at a significant cost to our understanding of spacetime. This idea suggests that the event horizon might not be the smooth, empty boundary predicted by classical general relativity. Instead, it might be a seething wall of high-energy particles that would incinerate anything attempting to cross it. While this firewall would prevent information from entering the black hole and thus resolve the information paradox, it would also violate the equivalence principle, one of the fundamental assumptions of general relativity. An astronaut falling toward a black hole would experience violent destruction at the horizon rather than the smooth passage that relativity predicts. The debate over firewalls illustrates how the event horizon continues to challenge our most basic assumptions about physics. It forces us to choose between cherished principles. Either quantum mechanics is wrong about information conservation, or general relativity is wrong about the nature of free fall, or our understanding of both theories is incomplete in ways we haven't yet grasped. These theoretical battles are fought with mathematical weapons of extraordinary sophistication, but they ultimately concern questions that touch the very heart of existence. What is the relationship between information and reality? Can knowledge be truly lost from the universe? Is spacetime fundamental or emergent? The event horizon stands at the center of all these mysteries, a cosmic Rosetta Stone that might one day help us decode the deepest secrets of nature. As we contemplate these profound puzzles in the gentle darkness of night, it's worth remembering that the same quantum fields that create virtual particles near event horizons also exist here in the space around you. The vacuum of space in your room is filled with the same quantum fluctuations, though they're far too subtle to detect without the most sensitive instruments. You're surrounded by the same fundamental physics that creates the mysteries of black holes, just expressed in gentler, more familiar forms. The event horizon reminds us that reality operates on principles far stranger than our everyday experience suggests. These invisible boundaries in space-time represent the limits of the classical world and the beginning of quantum mystery. They show us that the universe is not a collection of separate objects moving through empty space, but a unified whole where geometry, information, and quantum mechanics dance together in ways we're only beginning to understand. Tonight, as your thoughts drift towards sleep, you might imagine yourself floating gently through space, approaching one of these cosmic boundaries. As you draw near, time begins to behave strangely. Space curves in impossible ways, and the very concepts of inside and outside lose their meaning. You're not falling into darkness, but into mystery itself, where the familiar gives way to the profound and the known dissolves into wonder. In our next gentle exploration, we'll journey even deeper into these cosmic mysteries, examining how modern observations have brought us face to face with event horizons, and how future discoveries might finally resolve the paradoxes that have puzzled physicists for generations. Until then, rest well in the knowledge that the universe continues to hold secrets far more beautiful and strange than we have yet imagined. As we drift further into the gentle mysteries of these cosmic boundaries, let us explore something truly remarkable about how event horizons have transformed from pure mathematical abstractions into observable reality. In recent years, humanity has achieved something that would have seemed impossible just decades ago. We have actually seen the shadow of an event horizon itself. Picture, if you will, a global network of radio telescopes scattered across our planet, from the volcanic peaks of Hawaii to the frozen plains of Antarctica. Each telescope, working alone, could capture only fragments of the cosmic story, but when linked together through precise timing and sophisticated computer processing, they form a virtual telescope the size of Earth itself. This remarkable collaboration, known as the Event Horizon Telescope, has given us our first direct glimpse of these invisible boundaries. The images that emerged from this effort are both beautiful and haunting, We see a ring of glowing matter surrounding a dark, circular shadow, like a cosmic donut floating in the depths of space. That shadow isn't the black hole itself, but rather the silhouette cast by its event horizon as it blocks the light from the superheated material swirling around it. For the first time in human history, we can actually see the boundary where space-time curves so severely that light itself cannot escape. These observations reveal something profound about the nature of matter and energy near event horizons. The glowing ring we observe consists of gas and dust that has been accelerated to incredible speeds as it spirals inward toward the boundary. Friction between particles heats this material to temperatures of millions of degrees, causing it to shine brilliantly across the electromagnetic spectrum. Yet just inside that glowing ring lies the event horizon itself, invisible and impenetrable, marking the boundary beyond which no light can return to tell us what lies within. The precision required to create these images is almost beyond comprehension. The telescopes must be synchronized to within tiny fractions of a second, their data combined using atomic clocks that are accurate to billionths of a second. The computational processing required to extract the final image from the raw data involves algorithms that must account for the rotation of the Earth, the movement of the telescopes through space, and countless other subtle effects that could blur or distort the final result. But perhaps most remarkably, these observations have confirmed theoretical predictions made decades ago using nothing but mathematical reasoning. The size and shape of the shadows match almost exactly what Einstein's equations predicted they should look like. This represents a triumph of human reason, showing how pure mathematical thought can reveal truths about the universe that are later confirmed through direct observation. The black holes we've imaged are truly monstrous in scale. The supermassive black hole at the center of galaxy M87 contains about 6.5 billion times the mass of our Sun, compressed into a region smaller than our solar system. Its event horizon stretches across a distance that light would take about a day to traverse. Yet this entire boundary is invisible except for the shadow it casts against the glowing material around it. Closer to home, we've also captured images of Sagittarius A star, the supermassive black hole that lurks at the center of our own Milky Way galaxy. This cosmic giant, containing about 4 million solar masses, sits about 26,000 light-years from Earth, quietly anchoring our entire galaxy with its immense gravitational influence. The fact that we can image its event horizon despite this vast distance speaks to both the enormous size of these objects and the incredible sophistication of our observational techniques. These direct observations have opened entirely new avenues for studying the physics of event horizons. We can now watch as matter approaches these boundaries in real time, observing how it heats up, accelerates, and eventually disappears beyond the point of no return. We can study how the intense magnetic fields generated by this infalling matter interact with the curved space-time near the event horizon, creating jets of particles that stream outward at nearly the speed of light. The images also reveal the dynamic nature of these cosmic boundaries. The event horizon isn't a static, unchanging surface, but a living boundary that responds to the flow of matter and energy around it. As material falls in, the black hole grows slightly larger, and its event horizon expands accordingly. The boundary breathes and shifts with the rhythm of cosmic accretion, marking the ever-changing edge between the observable universe and the hidden realm within. But visual observations represent only one way we've learned to study event horizons directly. Another revolutionary window opened when scientists first detected gravitational waves, ripples in the fabric of space-time itself that propagate outward at the speed of light. These waves are created when massive objects undergo violent acceleration, and some of the most dramatic sources are colliding black holes whose event horizons merge in cosmic catastrophes of unimaginable power. When two black holes spiral toward each other over millions of years, they eventually reach a point where their event horizons touch and merge. This process releases more energy in gravitational waves than all the stars in the observable universe emit in light during the same brief interval. Yet because gravitational waves interact so weakly with matter, they pass through planets, stars, and entire galaxies almost without effect, arriving at Earth as incredibly subtle distortions in spacetime. The detectors that capture these waves represent marvels of precision engineering. They consist of laser beams bouncing between mirrors separated by several kilometers. When a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction, causing tiny changes in the distance between the mirrors. These changes are so small that they measure less than 1/10,000th the width of a proton, yet they can be detected and measured with extraordinary precision. The gravitational wave signals from merging black holes tell us remarkable stories about the nature of event horizons. In the final moments before two black holes merge, they orbit each other hundreds of times per second, their event horizons stretched and distorted by tidal forces. The waves they emit carry information about the mass, spin, and structure of each black hole, allowing us to study these objects with unprecedented detail. When the event horizons finally touch, something beautiful happens in the mathematics of spacetime. The two separate boundaries merge smoothly into a single, larger horizon surrounding both black holes. The new boundary settles into its final shape through a process called ringdown, where the merged black hole oscillates like a struck bell before returning to equilibrium. These oscillations also emit gravitational waves, providing yet another probe of event horizon physics. These observations have confirmed many theoretical predictions about black holes while revealing new mysteries. We've learned that stellar mass black holes can be much more massive than previously thought, with some containing 50 or more times the mass of our Sun. We've discovered that merging black holes can receive powerful kicks from their own gravitational wave emission, sending the final black hole racing through space at speeds of thousands of kilometers per second. Perhaps most intriguingly, we've begun to observe phenomena that probe the very nature of the event horizon itself. Some theoretical models predict that the merger of two black holes might create echoes in the gravitational wave signal, subtle distortions that would reveal quantum or other exotic effects near the event horizon. While these echoes haven't been definitively detected yet, future observations with more sensitive instruments may reveal whether the event horizon truly behaves as classical general relativity predicts. The combination of direct imaging and gravitational wave detection has ushered in a new era of event horizon astronomy. We can now study these cosmic boundaries through multiple channels of information, building up a comprehensive picture of how they behave under different conditions. This multi-messenger approach promises to reveal aspects of event horizon physics that would be impossible to study through any single observational technique. Future observations will push these techniques even further. Next-generation gravitational wave detectors will be sensitive enough to observe black hole mergers throughout the entire observable universe, providing vast samples for statistical studies of event horizon properties. Space-based detectors will access entirely new frequency ranges of gravitational waves, potentially revealing the mergers of supermassive black holes and other exotic phenomena. Similarly, improvements in telescope technology will allow us to image event horizons with unprecedented detail. Future arrays of radio telescopes may span multiple continents or even extend into space, providing resolution sharp enough to study the dynamics of matter as it approaches and crosses the event horizon. We may even be able to test the predictions of different theories of quantum gravity by observing subtle deviations from classical behavior near these boundaries. The marriage of theory and observation in event horizon physics represents one of the great triumphs of modern science. What began as abstract mathematical speculation has evolved into a rich observational science with practical applications. The techniques developed for detecting gravitational waves have found uses in other areas of physics and engineering. The data processing methods created for the Event Horizon Telescope have applications in medical imaging and other fields requiring the reconstruction of images from scattered data. More fundamentally, these observations have confirmed that our mathematical understanding of space-time and gravity captures something real and deep about the structure of the universe. The fact that Einstein's century-old equations correctly predict the appearance of event horizon shadows and the properties of gravitational waves from black hole mergers demonstrates the remarkable power of human reason to uncover universal truths through mathematical investigation. Yet, for all our observational success, the deepest mysteries of event horizons remain unsolved. We still don't know what happens to information that crosses the boundary. We don't understand how quantum mechanics and general relativity fit together in the extreme environment near the horizon. We haven't resolved whether the smooth space-time predicted by classical physics gives way to something more exotic at these cosmic boundaries. These remaining puzzles ensure that event horizon physics will continue to be an active frontier of research for many years to come. Each new observation brings the possibility of discovering something unexpected, some deviation from our current understanding that points toward deeper truths about the nature of reality. The event horizon stands as both a laboratory for testing our most fundamental theories and a gateway to new physics waiting to be discovered. As you rest here in the quiet darkness, surrounded by the familiar comfort of Earth's gentle gravity, it's remarkable to consider that the same mathematical principles governing these exotic cosmic boundaries also shape the world around you. The curvature of space-time that creates event horizons is present everywhere, creating the gravitational fields that keep the moon in orbit and your feet firmly planted on the ground. We inhabit a universe where the most extreme phenomena emerge naturally from the same elegant laws that govern everyday experience. The journey from theoretical prediction to direct observation of event horizons represents one of humanity's greatest intellectual achievements. It shows how patient, careful investigation can eventually reveal even the most hidden aspects of nature. The invisible boundaries that once existed only in the imagination of mathematical physicists have become observable reality, opening new windows into the fundamental structure of the cosmos. Tonight, as your thoughts drift gently among these cosmic mysteries, you might imagine the ancient light that began its journey from distant galaxies millions of years ago, finally arriving at your eyes after an epic voyage through the expanding universe. Some of that light may have passed near event horizons during its journey, slightly deflected by their gravitational influence, carrying with it subtle information about these cosmic boundaries. In our final gentle exploration, we'll contemplate what these discoveries mean for our understanding of the universe and our place within it, and how the mysteries of event horizons continue to challenge and inspire our quest to understand the deepest nature of existence itself. As we draw near the end of our cosmic journey tonight, let us pause to consider something truly profound about what these discoveries reveal regarding the fundamental nature of existence itself. You see, the event horizon isn't merely another astronomical curiosity to catalogue alongside distant galaxies and exotic stars. It represents something far more significant, a window into the deepest questions that have puzzled humanity since we first looked up at the night sky and wondered about our place in the vast cosmos. The revelations emerging from our study of these invisible boundaries challenge some of our most cherished assumptions about reality. For centuries, we've imagined space and time as the fixed stage upon which the cosmic drama unfolds. But event horizons reveal that this stage is anything but static. It breathes, curves, and responds to the actors performing upon it in ways that would have seemed like pure fantasy to earlier generations of scientists. Consider how this transforms our understanding of determinism and free will. In the classical world described by Newton's physics, if you knew the position and velocity of every particle in the universe, you could in principle predict the future with perfect accuracy. The universe was like a vast clockwork mechanism ticking along according to precise mathematical laws. But near an event horizon, even this deterministic picture begins to break down in fascinating ways. The quantum fluctuations that create Hawking radiation introduce an element of genuine randomness into the behavior of black holes. These fluctuations aren't simply due to our ignorance of hidden variables, as Einstein hoped. They represent true quantum uncertainty built into the fabric of spacetime itself. The event horizon becomes a place where the classical certainty of general relativity meets the probabilistic nature of quantum mechanics, creating a frontier where our understanding of predictability itself must evolve. This intersection of classical and quantum physics near event horizons has sparked some of the most innovative thinking in modern theoretical physics. String theory attempts to resolve the apparent contradictions by proposing that the fundamental constituents of reality are not point particles, but tiny, vibrating strings existing in higher dimensional space. In this framework, event horizons emerge as collective properties of vast ensembles of these quantum strings. Loop quantum gravity takes a different approach, suggesting that space-time itself has a discrete, granular structure at the smallest scales. Near an event horizon, where curvature becomes extreme, these quantum geometric effects might become important, potentially softening the classical singularities predicted by general relativity. The event horizon in this picture becomes less like a sharp boundary and more like a quantum membrane with complex internal structure. Other approaches focus on the role of information and computation in fundamental physics. If the universe is essentially a vast information processing system, as some theories suggest, then event horizons might represent natural boundaries in this cosmic computation. The apparent loss of information at these boundaries could signal the limits of what can be computed or known within our universe, rather than a violation of physical law. These theoretical developments reveal something beautiful about the nature of scientific progress. Each generation of physicists builds upon the work of their predecessors while pushing the boundaries of knowledge into new territories. Einstein's general relativity emerged from Newton's mechanics, but transcended it in ways Newton could never have imagined. Similarly, the quantum theory of gravity that will eventually emerge from our study of event horizons will likely transcend both general relativity and quantum mechanics while preserving their essential insights. The practical implications of this research extend far beyond abstract theoretical concerns. The technologies developed to study event horizons have already found applications in fields ranging from medical imaging to quantum computing. The mathematical techniques used to analyze black hole physics have illuminated problems in condensed matter physics, helping us understand exotic states of matter that might lead to new technologies. More profoundly, our study of event horizons has revealed deep connections between seemingly unrelated areas of physics. The relationship between black hole entropy and area has influenced our understanding of thermodynamics and statistical mechanics. The holographic principle has found applications in understanding strongly interacting quantum systems. These cross-pollinations demonstrate how fundamental research into seemingly esoteric phenomena can illuminate practical problems in unexpected ways. The philosophical implications run even deeper. If the holographic principle is correct and our three-dimensional reality is somehow encoded on a two-dimensional boundary, this would represent a fundamental revision in how we understand the nature of existence itself. The event horizon would become not just a boundary in space, but a boundary between different levels of reality, different ways of describing the same underlying truth. This perspective suggests that the distinction between observer and observed, between subject and object, might be less fundamental than we typically assume. If information about the interior of a black hole is encoded on its boundary, then the boundary and interior represent different descriptions of the same physical reality. Perhaps the same is true for our own relationship with the universe. We might not be separate observers studying an external cosmos, but rather integral parts of a unified whole that can be described from multiple complementary perspectives. The event horizon also raises profound questions about the nature of consciousness and experience. If someone falls past this boundary, their subjective experience continues normally even as they become forever cut off from external observers. This suggests that consciousness might have a more fundamental role in physics than we typically acknowledge. The boundary between different conscious experiences might be as real and important as the boundaries in space-time itself. As we've explored throughout our journey tonight, the event horizon challenges our understanding of causality in ways that ripple through our entire worldview. The breakdown of the usual relationship between cause and effect near these boundaries forces us to reconsider basic questions about the flow of time and the nature of temporal experience. Perhaps our intuitive understanding of time as a flowing river needs to give way to something more subtle and complex. The study of event horizons has also revealed the importance of observer perspective in fundamental physics. The fact that different observers can disagree about basic facts, such as whether an event horizon exists or whether information has been destroyed, suggests that reality might be more observer-dependent than classical physics assumed. This doesn't mean that physics is subjective or that anything goes, but rather that the objective truth might be richer and more subtle than any single perspective can capture. These insights connect to broader questions about the role of intelligence and observation in the universe. If conscious observers play a fundamental role in determining physical reality, as some interpretations of quantum mechanics suggest, then the event horizon becomes a natural laboratory for studying these connections. The boundary between what can be observed and what remains hidden might reflect deeper truths about the relationship between mind and cosmos. Looking toward the future, the mysteries of event horizons will likely continue to drive fundamental research in physics for generations to come. The development of quantum computers might provide new tools for simulating the complex quantum dynamics near these boundaries. Advances in artificial intelligence might reveal new patterns in the vast datasets generated by gravitational wave detectors and telescope arrays. Space-based observatories might extend our reach to previously inaccessible regions of the electromagnetic spectrum. But perhaps most importantly, the study of event horizons reminds us that the universe still holds profound mysteries waiting to be discovered. Each answer we uncover reveals new questions that challenge our understanding in unexpected ways. The boundary between the known and unknown continues to expand, but it never disappears. There will always be new horizons to explore, new puzzles to solve, new truths to uncover about the nature of existence. As you rest here in the gentle darkness of night, surrounded by the familiar comfort of Earth's gravitational embrace, it's remarkable to consider that the same fundamental forces and principles that create these exotic cosmic boundaries also shape every aspect of your daily experience. The quantum fields that produce virtual particles near event horizons also course through the atoms in your body. The curved space-time that creates these mysterious boundaries also guides the light from distant stars to your eyes. We are not separate from the cosmic phenomena we study. but intimately connected to them through the universal laws of physics. The event horizon stands as a reminder that we inhabit a universe far stranger and more wonderful than our everyday experience suggests, yet one that remains comprehensible through patient observation, careful reasoning, and mathematical insight. The journey from the first theoretical prediction of black holes to our current ability to observe their event horizons directly represents one of humanity's greatest intellectual achievements. It demonstrates the power of human curiosity to uncover truths about nature that seemed forever beyond our reach. The invisible boundaries that once existed only in the realm of mathematical abstraction have become observable reality, confirming our faith in the power of reason to illuminate even the darkest corners of the cosmos. Tonight, as your consciousness drifts gently towards sleep, you might imagine yourself floating peacefully near one of these cosmic boundaries, watching as space-time curves and flows around you like a gentle cosmic tide. You're not falling into destruction, but into mystery itself, where the familiar concepts of space and time dissolve into something far more profound and beautiful. The event horizon awaits, patient and eternal, holding its secrets at the very edge of human understanding. It reminds us that the universe is not a puzzle to be solved once and for all, but an endless source of wonder that will continue to challenge and inspire curious minds for as long as humans gaze up at the stars and ask the fundamental questions about existence, reality, and our place in the vast cosmic story that continues to unfold around us. Sweet dreams, fellow travelers of the cosmic frontier. May your rest be peaceful, and may you wake tomorrow with renewed wonder at the magnificent mysteries that surround us in this strange and beautiful universe we call home. In these quiet moments before sleep, as we float gently through the final passages of our cosmic exploration, let us turn our attention to something deeply personal about these mysterious boundaries. You see, the event horizon doesn't just exist in the distant reaches of space, marked by exotic mathematics and observed through sophisticated instruments. It exists as a metaphor for the boundaries of human experience itself, the edges of what we can know, feel, and understand about our place in this vast universe. Consider how the event horizon mirrors the boundaries we encounter in our own consciousness. Just as there are regions beyond the black hole's boundary that remain forever hidden from external observers, there are aspects of our own inner experience that can never be fully shared or communicated to others. Your dreams, your deepest thoughts, the precise quality of your subjective experience of color or music or love, these remain trapped within the event horizon of your individual consciousness, accessible only to you. Yet unlike the stark finality of a black hole's boundary, the horizons of human experience are permeable in beautiful ways, through art, through science, through gentle conversations in the quiet hours of night. We manage to transmit something of our inner worlds across the boundaries that separate one consciousness from another. Poetry becomes a kind of hawking radiation for the soul, carrying encoded information about experiences that would otherwise remain forever hidden. The mathematics that describe event horizons reveal something profound about the nature of boundaries themselves. In our everyday world, we're accustomed to sharp divisions between inside and outside, between here and there, between now and then. But near these cosmic boundaries, such distinctions become fluid and observer-dependent. The boundary exists differently for different perspectives, reminding us that even the most fundamental aspects of reality might be more malleable than we typically assume. This fluidity extends to our understanding of information itself. We've explored how the information paradox challenges our assumptions about what can be lost from the universe. But perhaps this puzzle reflects something deeper about the nature of knowledge and memory. In our own lives, we constantly lose information to the passage of time. Childhood memories fade, learned skills atrophy, entire languages can disappear from communities. Yet something essential seems to persist, encoded perhaps in ways we don't fully understand. The holographic principle suggests that information about a black hole's interior might be encoded on its boundary surface. Similarly, perhaps the information that shapes who we are is encoded not just in our brains, but in the patterns of our relationships, the ripples we create in the lives of others, the subtle ways we influence the world around us. The boundary between self and environment becomes as permeable and complex as the boundary around a black hole. These cosmic phenomena also invite us to reconsider our relationship with time itself. Near an event horizon, time behaves in ways that challenge our intuitive understanding of duration and sequence. Different observers experience the same events at dramatically different rates, creating multiple valid descriptions of temporal reality. Perhaps our own experience of time is similarly subjective and malleable, shaped by attention, emotion, and the quantum fluctuations of consciousness itself. In the gentle hours before dawn, when the boundary between waking and sleeping becomes soft and permeable, we might catch glimpses of this temporal fluidity in our own experience. Dreams unfold in their own time frame, where minutes can contain lifetimes and hours can pass in an instant. Memory operates by its own temporal logic, bringing distant events into vivid present reality, while allowing recent experiences to fade into background noise. The study of event horizons has revealed that even the most extreme boundaries in nature are not walls, but interfaces, places where different descriptions of reality meet and interact. The same might be true for the boundaries in our own experience. The division between conscious and unconscious, between rational thought and intuitive knowing, between self and other, these might be interfaces rather than barriers, places where different aspects of experience can interact and exchange information in subtle ways. Modern observations have shown us that event horizons are not static, unchanging boundaries but dynamic features that respond to their environment. They grow when matter falls in, oscillate when disturbed, and even merge with other horizons in cosmic dances of unimaginable complexity. Perhaps the boundaries of our own awareness are similarly dynamic, expanding through experience, contracting through fatigue, merging temporarily with others through empathy and connection. The detection of gravitational waves has revealed that even the most violent cosmic events, the merger of black holes whose event horizons collide and combine, create ripples that propagate gently through space-time, barely disturbing the fabric of reality as they pass. These waves carry information across vast distances, connecting events separated by billions of light-years through subtle distortions in space and time. In our own lives, we create similar ripples through our actions and choices. The kindness shown to a stranger, the curiosity that drives us to learn something new, the gentle attention we pay to these cosmic mysteries in the quiet hours of night, all of these create waves that propagate outward through the social fabric of human experience. Like gravitational waves, these influences might be subtle and difficult to detect, but they carry information and energy across the boundaries that seem to separate us from one another. The quantum nature of event horizons, with their Hawking radiation and information paradoxes, reminds us that even at the most fundamental level, reality is characterized by uncertainty and creativity rather than rigid determinism. The virtual particles that pop into existence near these cosmic boundaries mirror the spontaneous insights that emerge at the edges of our own understanding, the sudden connections and intuitions that seem to arise from nowhere yet carry profound truth. Perhaps consciousness itself operates through similar quantum processes, with thoughts and feelings emerging from the vacuum of awareness like virtual particles near an event horizon. Some of these mental events find expression in the world through speech or action, while others remain forever internal, contributing to the hidden dynamics of inner experience. The holographic principle, which suggests that three-dimensional reality might be encoded on a two-dimensional boundary, offers a beautiful metaphor for how meaning and significance can emerge from apparently simple information. A poem consists of nothing but marks on paper or sounds in air, yet it can encode entire worlds of experience and emotion. A scientific equation might contain only a few symbols, yet it can describe phenomena spanning the entire universe. Similarly, the event horizon might appear to be a simple boundary in space, but it encodes information about the entire history of everything that has ever approached it. In our own lives, the present moment might seem like a simple boundary between past and future, yet it contains within it the accumulated wisdom of all our experiences and the potential for all our future choices. The study of these cosmic boundaries has required humanity to develop new technologies and new ways of thinking that push the limits of what seemed possible. The Event Horizon Telescope required international cooperation and precise coordination across multiple continents. Gravitational wave detectors demanded engineering precision beyond anything previously achieved. These accomplishments remind us that the most profound mysteries often require collaborative effort and patient dedication spanning many years or decades. In our personal exploration of life's mysteries, we might adopt similar approaches. The deepest questions about meaning, purpose, and connection often require patient attention and collaboration with others who share our curiosity. Like astronomers combining data from multiple telescopes to create a clearer image, we might combine insights from science, art, philosophy, and personal experience to develop a more complete understanding of our place in the cosmic story. The fact that we can study event horizons at all, despite their inherent hiddenness, demonstrates the power of indirect observation and mathematical reasoning. We cannot see inside a black hole, but we can study the matter swirling around it, the gravitational waves produced when they merge, the subtle bending of light in their vicinity. These indirect methods reveal truths that would be impossible to observe directly. Perhaps the same approach can illuminate the hidden aspects of our own experience and relationships. We cannot directly observe another person's consciousness, but we can study the patterns of their behavior, the ripples they create in the world around them, the ways they respond to different situations. Through patient observation and empathetic reasoning, we can develop understanding that transcends the boundaries of individual experience. The event horizon also teaches us about the importance of perspective in understanding complex phenomena. The same boundary appears completely different to observers in different reference frames, yet both perspectives capture essential truths about the underlying reality. This suggests that many of the disagreements and conflicts in human experience might arise from the fact that we're observing the same reality from different vantage points, each valid within its own framework, but incomplete when taken alone. The collaborative nature of modern event horizon research, involving theorists, observers, and engineers from around the world, demonstrates how the most challenging questions often require diverse perspectives working together. The mathematical physicist brings one kind of insight, the observational astronomer another, the engineer yet another. When these perspectives are combined thoughtfully, they create understanding that none could achieve alone. As we rest here in the quiet darkness, feeling the gentle pull of Earth's gravity that keeps us safely anchored to our planet's surface, we can reflect on how the same fundamental forces that create these exotic cosmic phenomena also shape our everyday experience in subtle but profound ways. The curvature of spacetime that becomes extreme near event horizons is present everywhere, creating the gravitational fields that allow planets to form, stars to shine, and life to emerge and flourish. We are not separate observers studying a distant universe, but integral participants in the cosmic story itself. The atoms in our bodies were forged in the hearts of ancient stars, some of which may have ended their lives by collapsing into black holes. The light that illuminates our world has traveled across vast distances, sometimes passing near these cosmic boundaries and carrying with it subtle information about the extreme physics that governs them. The event horizon stands as a perfect symbol for the boundaries of knowledge itself. It marks a place beyond which certain kinds of information cannot reach us, yet its very existence teaches us profound truths about the nature of space, time, and reality. Similarly, the limitations of human understanding, rather than being obstacles to overcome, might be features that give meaning and mystery to our existence. Tonight, as consciousness gently approaches its own event horizon between waking and sleeping, we can appreciate how these cosmic mysteries connect to the most intimate aspects of our experience. The same quantum uncertainty that creates virtual particles near black holes might contribute to the spontaneous creativity of dreams. The same geometric inevitability that characterizes paths inside event horizons might govern the unfolding of deep sleep, where conscious choice gives way to unconscious processing. In those liminal moments between sleep and waking, we might catch glimpses of what it means to exist at the boundary between different states of being. Like matter approaching an event horizon, our conscious awareness slows and redshifts as it approaches the boundary of sleep, eventually disappearing from the perspective of waking observation, yet continuing its journey into hidden realms of experience. The event horizon reminds us that the universe is full of boundaries that are not walls but gateways, not endings but transformations. As we cross the threshold into sleep tonight, we embark on our own journey beyond an event horizon of consciousness, carrying with us the wonder and mystery of these cosmic phenomena into dreams where space and time behave by their own strange logic. Rest well, knowing that somewhere in the vast darkness, invisible boundaries continue to mark the edges of the knowable universe, holding within their mathematical embrace secrets that connect the largest scales of cosmic structure to the most intimate mysteries of consciousness and experience. The event horizon awaits, patient and eternal, at the intersection of physics and poetry, where the story of the universe touches the story of every dreaming mind beneath the star-filled sky. Sweet dreams, fellow travelers of the cosmic frontier, knowing that the event horizon will continue its eternal vigil at the edges of space-time, holding secrets that bridge the vastness of the universe with the intimate mystery of your own consciousness. In these final moments of our gentle journey together, as we float softly back from the brink of cosmic mystery toward the familiar comfort of earthly rest, let us carry with us the profound realization that we have touched something truly extraordinary tonight. The event horizon, that invisible threshold around black holes, has revealed itself to be far more than just another astronomical curiosity catalogued in the margins of textbooks. We have discovered that these boundaries represent nothing less than the frontier of human understanding itself, places where our most fundamental assumptions about reality are stretched, challenged, and ultimately transformed. In exploring these cosmic edges, we have not merely learned about distant objects in space, but about the very nature of existence, information, and the strange relationship between observer and observed that defines our place in the universe. The mathematical poetry of these invisible boundaries speaks to something deep within the human spirit, our endless quest to understand not just how the universe works, but why it works the way it does. From Einstein's elegant equations to Hawking's profound insights about thermal radiation, from the holographic principle to the information paradox, each discovery has peeled back another layer of cosmic mystery while revealing new depths waiting to be explored. Perhaps most remarkably, we have seen how the extreme physics governing these distant boundaries connects intimately to the quantum foundations of reality that operate everywhere, including in the atoms of your own body and the neural pathways of your dreaming mind. The same principles that create event horizons also shape the familiar world around you, reminding us that we are not separate from the cosmic phenomena we study, but woven into the very fabric of space-time itself. The recent triumph of directly observing these boundaries through the Event Horizon Telescope and detecting their gravitational wave signatures has marked a new chapter in humanity's relationship with the cosmos. We have moved from pure mathematical speculation to direct observation, confirming that the strange predictions of general relativity hold true even under the most extreme conditions imaginable. Yet for all our observational success and theoretical sophistication, the deepest mysteries remain beautifully intact. The information paradox continues to challenge our understanding of what can be known and what must remain forever hidden. The quantum nature of space-time near these boundaries hints at new physics waiting to be discovered. The relationship between consciousness and observation takes on new meaning when contemplated in light of these cosmic phenomena, where different perspectives yield fundamentally different descriptions of reality. As you drift gently towards sleep tonight, carried along by the same gravitational forces that create these magnificent cosmic boundaries, remember that you are participating in one of the universe's most remarkable features, the emergence of consciousness capable of contemplating its own origins and destiny. Through patient observation, mathematical reasoning, and collaborative effort spanning generations, humanity has managed to peer into realms that seemed forever beyond our reach. The Event Horizon stands as a testament to both the power of human curiosity and the enduring mystery that surrounds us. It marks not just a boundary in space, but a boundary in knowledge itself, reminding us that the universe will always hold secrets waiting to be discovered by future generations of curious minds. In those quiet moments just before sleep claims you completely, when the boundary between waking consciousness and dreams becomes soft and permeable, you might reflect on how these cosmic mysteries connect to the most intimate aspects of your own experience. The same quantum uncertainty that governs virtual particles near event horizons might contribute to the spontaneous creativity of your dreams. The same geometric inevitability that characterizes the interior of black holes might govern the peaceful surrender of consciousness to sleep's gentle embrace. Tonight, you rest in a universe far stranger and more wonderful than our ancestors could have imagined, where invisible boundaries mark the edges of the knowable, where information might be preserved in ways that transcend ordinary space and time, and where the deepest truths about reality emerge from the marriage of mathematical reasoning and careful observation. The event horizon awaits, patient and eternal, holding within its invisible embrace secrets that connect the largest scales of cosmic structure to the quantum foundations of existence itself. It reminds us that we inhabit not just a universe of matter and energy, but a universe of information and consciousness, where boundaries are not walls, but gateways to deeper understanding. Thank you for joining me on this peaceful journey to the very edges of human knowledge. I hope these cosmic mysteries have provided a gentle bridge between the wonder of scientific discovery and the tranquil embrace of restful sleep. Whether you found yourself captivated by the profound puzzles we've explored or peacefully lulled by the rhythmic flow of cosmic contemplation, know that you've participated in humanity's grandest adventure, the quest to understand our place in the vast, mysterious, and utterly magnificent universe we call home. Until we meet again among the stars and equations, the telescopes and theories, rest well in the knowledge that somewhere in the cosmic darkness, event horizons continue their eternal dance at the boundaries of space-time, holding secrets that may one day illuminate not just the nature of black holes, but the deepest questions about existence, consciousness, and the beautiful mystery of being aware in a universe that somehow managed to become aware of itself. Sweet dreams, and may your rest be as peaceful as the gentle curvature of space-time that cradles us all in its cosmic embrace. This has been another journey into the sleepy science that surrounds us, where curiosity meets tranquility under the vast canopy of night. Good night.